In this segment of our lecture on random walk-based algorithms for property testing, we are going to look at an algorithm to test whether a given graph is either bipartite or far from being bipartite. So we're going to be using random walks, but we need to be a bit careful here because we're dealing with bipartite graphs. Now, let's assume that the graph is d-regular, and it's possibly a bipartite graph because one of the two options that we have in the promise given to us that it's either bipartite or far from being bipartite. And we also have the promise that a random walk on this graph will mix rapidly. But we need to be a bit careful here because the traditional random walk is actually a periodic Markov chain in this context because the graph could be a bipartite graph. Now, how do we ensure that it becomes aperiodic? And for that, we're not going to use the traditional random walk, but rather we're going to use what is called a lazy random walk. So let's consider a vertex V, and it has degree V, number of edges incident at it. It could be, if it's d-regular, degree of V will be exactly d, but even otherwise, you can think of d as being an upper bound on the degree, and so the individual degrees can be something between 1 and d. So here is a vertex V with degree V number of edges incident at it. So the question now is, how are we going to assign the transition probabilities? So what we're going to do is we're going to, instead of transitioning with probability 1 over the degree of the vertex V, we're instead going to transition to neighbors with probability 1 over 2 times d, where d is the max degree. So every edge incident at V gets a probability of 1 over 2d. But this leaves us with some remaining probability, and with that probability, 1 minus the degree of V over 2d. So this is the probabilities that have been exhausted by considering all the edges incident at V. So 1 minus of that is the remaining probability, and with that probability we're just going to remain in the vertex V. So you can see why such a random walk is called lazy, because there's a probability of at least half that the walk will actually stay in the same vertex. It won't move with that much probability. And the important thing to keep in mind is that no longer is the Markov chain periodic. So you may want to pause for a little while to convince yourself of this fact. We are now ready to dive into the problem. So let's make sure we understand the problem statement precisely. So the input is a graph G equals V comma E in the bounded degree model. And in this model, our queries are of the form, what is the ith neighbor of vertex V? And also we may need to also find out what the degree of each vertex V is. And so this is the bounded degree model in property testing for graphs. And we're given two promises. The first promise that the graph G is either bipartite or far from being bipartite. And what exactly do we mean by far from being bipartite? So at more than epsilon dn edges must be removed to make G bipartite. And here epsilon is just some fixed constant greater than 0. The second promise that we have is that the lazy random walks mix quickly in this graph. And in particular, the promise is that a lazy random walk, as we have described just a little while ago, will mix within O of 1 over epsilon polylog of n number of steps. Which, recall, what does it mean for a random walk to mix? It just means that the random walk will reach a probability distribution that's very close to the stationary distribution within this amount of time. So here's the algorithm that we have for this problem. And you may want to recollect that a graph is bipartite if and only if it has no odd cycle in it. So we're going to really take advantage of that, and for that, so here's the key subroutine in this algorithm. The subroutine is called odd cycle. So how does it go? We first pick a node S in the graph, and this node, let's say, is chosen uniformly at random. And now we perform some number of lazy random walks. In particular, we will be performing square root of n and times polynomial in 1 over epsilon log n number of random walks starting from S. And each of these random walks will be of length L, and that L is going to be a polynomial in 1 over epsilon times log n. And recall that this is going to be sufficient amount of time for the random walk to mix. So we're going to generate k such random walks, and then we're going to observe something about these random walks. We're going to see if there exists some vertex v such that this vertex was reached by both an odd and an even length random walk. And here's something that we need to be a bit clear about. Now let's go back to the notion of lazy random walk. What we're counting as the length of the walk is the actual number of steps taken, excluding these self loops that we have over here. So coming back to the algorithm here, a walk that actually made L steps need not actually be of length L, because there could be several self loops involved. And what we are interested in is the length without the self loops being considered. And there's two possibilities. Either that length can be odd or even. And we want to know whether there was a vertex v that was reached by both an odd and an even length prefix. Okay. If such a vertex v can be found, then clearly what we can conclude is that there exists an odd cycle. So we will return saying we have found an odd cycle, in which case eventually we will reject this graph. If we did not find such a vertex v, then we'll have to show subsequently that it's likely that this graph does not have an odd cycle, and therefore we will just return for now that there is no odd cycle. And now what we do is we just embed the odd cycle subroutine within a wrapper. All we do in this wrapper is that we execute the odd cycle subroutine sum O of 1 over epsilon times, and then we wait to see if there's any one odd cycle call that comes back with saying that it found an odd cycle. If it found an odd cycle, then we will immediately reject. If, on the other hand, none of the calls to odd cycle came up with a found return value, then that means all of them came with the not found return value from the subroutine. Then we will accept this graph as being a bipartite graph. Of course, clearly this graph is always going to be correct if the input graph is this algorithm is always going to be correct if the input graph is bipartite. So our analysis, moving into analysis, all we need to do is focus on proving that graphs that are epsilon far from being bipartite will be rejected. And this we will want to reject with some constant probability, let's say 2/3. Now recall that the type of random walk we used is a lazy random walk, and we picked a vertex S and we started making a random walk, and we eventually landed at some vertex V, and along the way we might have taken several self loops, which we are simply not going to count in terms of the length of the walk from S to V. Now the length of the random walk, the number of steps taken by the random walk, is some polynomial in a small typo here, polynomial in log n over epsilon. Okay, so with that, let's look at this random walk. Let's look at the characteristics a little carefully. Let's denote by PV the probability that the random walk will terminate at V. And remember this, we assumed that the random walk was of the lazy type. A quick exercise for you is to convince yourself that such a lazy random walk will actually have a stationary distribution that's uniform over all the vertices. Now you may want to pause and convince yourself that that's the case. Now having convinced yourself that the stationary distribution under a lazy random walk is actually the uniform distribution, and the fact coupling that with the fact that our random walks have walked for mixing time number of steps, we can assume that a PV, the probability that the random walk will be at V, is close to 1 by n. And in particular, let's say that it's within one half of 1 by n to at most twice of 1 by n. Okay. Now this PV, we're going to break that up into two parts. Remember, we want to eventually argue something about walks that took an even number of, walks of even length versus odd length. So what we're going to do is we're going to break up PV into two parts. PV with a superscript E refers to the probability that the random walk will terminate at V, and the walk length, and this is the walk, not the random walk number of steps by the random walk taken by the random walk, but the walk length, which is obtained by ignoring the self loops, is even. So this is the probability that you started at S and you made an L length random walk, including some self loops, and then you reached at V. And if you remove all the self loops and just look at the length of the walk from S to V, this walk was of even length, and you landed in V. So this is the probability of that event. And similarly, you can define PV superscript O for odd, which is exactly the same event except that the length of the walk is now odd. Clearly, PV superscript E plus PV superscript O both add up to PV, and we know that PV is at least 1 over 2n. Now, with this notion of lazy random walks and the notation that go along with it, we're now ready to look at the framework of our analysis. So how are we going to do this analysis? So there's going to be a very, very key summation. This is the summation over all the vertices of the product PVE times PVO. Now think about this to understand what this summation is about. If the graph is a bipartite graph, for each vertex V, either PV of E is 0 or PV of O is 0, because each starting at S, each other vertex can only be reached by either an even length path or an odd length path. So one of these probabilities is going to be 0 if the graph is bipartite. So the entire summation is going to be 0. However, this summation, let's consider what happens when the graph is epsilon far from being bipartite. Now, we need to show then that this summation is actually going to be large. And by large, we mean that it is greater than some epsilon over C prime n. And moreover, if it is large, we need to be able to say then that this function odd cycle will return a found verdict with some constant probability. So let me repeat that again. So when this summation, when the graph is, when the given graph is far from being bipartite, then this summation starts to take a larger value. It's certainly not 0, so it starts to take a much larger value. And in particular, we want to show that this summation takes some value greater than epsilon over C prime n, and C prime is some constant. And if you can, given that the summation is so large, we need to be able to show then that the odd cycle subroutine will return a found verdict with some significant probability. And this is the 2 steps of the analysis that we are going to follow. So without further ado, let's start with step 1 and recollect what is it that we want to show. We want to show that if the graph is epsilon far from being bipartite, then this summation over all these vertices, PVE times PVO, is at least epsilon over Cn, where C is some constant. Okay, but what we will show is, well, this is a standard proof technique. We will show that under the assumption, that if we start with the assumptions that the summation is actually small, as in less than epsilon over Cn, and the graph is far from being bipartite, we can work our way to a contradiction. So if you think about this, when this leads to a contradiction, what we have proved is the negation of this statement that we have over here, and the negation of the statement is the negation of this individual statement or this statement. And the negation, and if you work it out, it's exactly going to be logically equivalent to this implication. Okay, so let's move on. And just the things that you need to keep in mind is that we are assuming that this summation is small, that is less than epsilon over Cn, and the graph is epsilon far from being bipartite. Okay, so keep that in mind. So with that, let's start with the analysis. Of course, in the odd cycle subroutine, we first pick an S, and this you can think of it as a sort of an enforce step, because the moment you pick S, you can then split the vertex set into two, partition the vertex set into 2 parts, VE and VO. But this is not just done arbitrarily, but rather this is done in the following manner. So this is the set VE is the set of all vertices such that the probability PVE is greater than or equal to PVO. So these are the vertices such that you are more likely to terminate at them with an even number of steps, So that's, and remember, if it's a bipartite graph, so every step will take you from one part to the other part. So so that makes a lot of sense, because now you're more likely in even steps to be on the left part. That's at least what we hope, if this is a proper way to partition this graph. So this is VE, and anything other than VE we place in VO. So these are going to be vertices that are more likely to, for the random walk to terminate, having a walk length that's of odd length. Well, let us now pick a vertex V. This is some vertex V. For convenience, we placed it in VE, but later we can see that it could be even in VO. But what do we know about V? Well, PV superscript E is at least 1 over 4n. Why? Well, without the E superscript, that itself is going to be 1 over 2n, and moreover we know that PV is equal to PVE plus PVO, and we know that on the left side PVE dominates, and so if you think about it, PVE must be at least 1/4 of 1 over n. Okay, now consider the neighborhood of V. So just to let you know where we are going, we're trying to find the product of PVE times PVO. Now, well, PVE we already have, but to get to PVO, we're going to try and get a bound on PVO by looking at the neighborhood of V and seeing what is the probability of reaching the neighborhood as an even number of steps, because once you reach a neighborhood with an even number of steps, then in one step you will reach V, and then that will be a way to reach V with a walk that's of odd length, and so that will give us PVO. So that's really where we're going. So let's go one step at a time. So let's pick a vertex U that's a neighbor of V. And let's focus in particular on the neighborhood of V within the set VE here. So these are the neighbors. So V might have neighbors over here, but we're not going to worry about that. And we know that under the same reasoning, we know that PUE is at least 1/4 1 over 4n. And here's something we need to prove. So this is going to be left as an exercise, but it's a nice little exercise for you to think about. What we need to show is the probability that a random walk starting at S will reach U with an even number of with a walk length that is of even parity in L-1 random walk steps. So here we're adding a little parameter to this probability. Here we're specifying that the number of random walk steps should be L-1. And this probability, we want to understand this. And our claim is that this probability is not too small. It's at least 1 over 32n. So think about this. The hint that I would like to give is that basically we know this PU superscript E is at least 1 over 4n. Now this you'll reach U having taken several self loops. So the probability of reaching having the same walk structure but achieving that in L-1 random walk steps is you can achieve that by just skipping one of the self loops, if you will. So exploiting that, we want to get a bound on this probability, and we want to be able to say that that's at least 1 over 32n. So this is your exercise. And now let's proceed with this bound. So now uh, notice that if with this bound, what that means is we have reached U uh, with some probability 1 over 32n, and then in one step we can and we've reached U with a walk length that is of even length up to U, which means that with 1 over 2d probability we will step into V, and by doing so we would have reached V with a walk length that is odd. So that gives us therefore a bound for this probability PVO. So PVO, now we looked at one particular U, but now we have to sum over all neighbors of all U that are neighbors of V, but in restricted to this VE. So summation over all such U. This is the probability that we already have over here, that we will reach U with an even length walk in L-1 random walk steps. And then with probability 1 over 2d, we will transition into V. And summed over all U, we will get a bound for a lower bound for PVO. Okay, and now remember we have a notation dE of V for the number of neighbors of V that are in this set VE. So this therefore this is simply dE of V times, and now we're going to plug in this inequality of 1 over 32n over here. This 2 here will make this a 64, so we get this bound over here. So notice now that we have a bound for PVE and we have a bound for PVO. So these are the two components that we need to multiply, and we are interested in PVE times PVO. So all we need to do is, well, this is nothing but 1 over 4n times that's basically PVE times this bound over here, DEV over 64dn. And just to be clear, this must not be an equal to, but rather an inequality. One last comment here. This exact same argument can be repeated for vertices on the right side as well. So the same expression, except now we won't have DEV, but we'll have DOV, because it's now if the vertex V was chosen on the right side, then we'll be interested in neighbors that are on the right side. So that will be DO of V. So barring that change, this expression will remain exactly the same. So we can actually put it back into the put this expression back into this larger summation. Remember, we were interested in the summation over all the vertices, PVE times PVO, and this summation is at least the sum of these individual summations. The first summation is simply based on what we have over here, and the second summation is what we would have if we considered the vertices to be the vertex V to be drawn from here. So that's essentially what we have over here: V drawn from V in VE and V in VO. But the expression inside the summation is pretty much identical, except that we are using DOV here because that's the number of neighbors of V in VO, given that V is in VO. So now, pulling out the common terms, we get 1 over some constant C prime D n squared outside, and then we have the summation over vertices in VE, summation over vertices in VO, the neighbors of DEV and the neighbors of V, DEV, and in the set VE, and here in the set VO. What exactly is the summation? Well, this is, as it turns out, simply the number of violating edges for the partition VE and VO. Why is that? Well, think about this. This is if that partition, consider the partition VE and VO. These are the neighbors within the same partition. So these are the violating edges. And this number of violating edges must be at more than epsilon dn. That's the assumption that we started off with. So if we plug this epsilon dn over here, we will end up getting a bound of epsilon over c prime n, because this dn will cancel out with this d and one of these n's. So we'll be left with this summation being at least epsilon over some c prime n. But keep in mind, our assumption was that this giant summation is actually less than epsilon times Cn. And this is our assumption that we started off with. Now, if C prime here is small, then this quantity is going to be larger compared to this epsilon Cn. And that would lead to a contradiction, because on the one hand, our assumption is that the summation is less than this smaller quantity. On the other hand, what we have worked out is that the summation is greater than this larger quantity. So this is the contradiction that we have established. So with this contradiction, the first step in our analysis is over, and we need to move on to the second step. So just to remind ourselves, the conclusion in the first step is that if the graph is epsilon far from being bipartite, then this summation will be large, will be more than some epsilon c prime n. And given that it's large, now our second step is to prove that the function odd cycle will actually return saying that an odd cycle is found with probability at least some constant. Okay, and by constant that means we're saying that it's bounded away from 0. Okay, so now let's move into step 2 of the analysis. So just to remind ourselves, we are given that the summation overall V, PVE times PVO is greater than or equal to epsilon over Cn. And we need to show that the odd cycle will find a bipartite, find an odd, will with good probability find an odd cycle, and therefore say return that it's found one. Okay, so now let's define an indicator random variable. This indicator random variable eta ij will be set to 1 if the ith and the jth random walk from S terminated at V, and one of them was of even walk length while the other was odd. So clearly you can see why this indicator random variable is important, because if this is if eta ij is 1, that means we have found a candidate vertex V, which gives us a witness to the fact that there is an odd cycle, and therefore we will be able to reject this graph. Okay, so eta ij takes on the value 1 under that condition, and otherwise it takes on the value 0. So what is the probability that eta ij equal to 1? That's nothing but, for eta ij to be 1, there must be some vertex V such that one of the probabilities. So let's pick up a vertex V. With probability PVE, the random walk will reach V, having a walk length that is even. With PVO, with this probability it will reach vertex V with a walk length that's odd. So if let's say the ith vertex, the ith random walk followed this probability and the jth random walk followed this probability, what you end up having is evidence of an odd cycle. The other option is that the the jth random walk follows this probability, and ith random walk follows this probability. So that's why we have this 2, because there's 2 ways in which these can combine. And that's just for one vertex v. And we have to therefore sum over all possible destination vertices v. And this summation is it gives us the probability that eta ij equals 1. And this is nothing but the expectation on the value of eta ij as well. Okay, and that simply follows from the fact that eta ij is an indicator random variable. And now notice that at the end we let's count all the eta ij's, all the possible eta ij's. Okay, now if the summation over all eta ij's where I is strictly less than j, if this summation is equal to 0, what that means is none of the pairs of walks terminated at the same vertex with different parity lengths. So we've not been able to find any evidence that the graph is not bipartite, which means that we will fail to reject. And remember, we're, of course, this whole analysis is under the assumption that the graph is actually far from being bipartite. So this would be the bad event. If this event were to occur, then we have our algorithm is incorrect. And so we need to ensure that this the probability of this event is small. Let's consider the probability of the complementary event. The total number of walks, remember, is some polynomial in 1 over epsilon times log n, the whole times square root of n. So this, I mean, the most important term to keep in mind is this square root of n over here. So there's the square root of n random walks means that the total number of pairs is at least k squared, big omega of k squared. Okay, which means that the number of pairs, if considering that that k is square root of n, is big omega of n over epsilon. So there's also this. Keep in mind that there's this epsilon over here. With that, let's consider the expectation of the sum of the eta ij's. That's, of course, bilinearity of expectation, nothing but the summation over all I less than j, expectation of eta ij. And, of course, the eta ij, the expectation of eta ij, if you recall, is this quantity 2pve times pvo summed over all vertices. And remember that this is now, we're now assuming that this is large. So at least some epsilon over Cn. So with that assumption, this expectation is going to be epsilon of the order of epsilon over Cn, but then we're summing over all pairs, and that's going to be big omega of n over epsilon. So some of the term, the n and the epsilon will cancel out, and this expectation will be some theta of 1 term. So it's going to be greater than 1, assuming the constants are appropriately chosen. But this doesn't give us enough strength, because now notice that this only says that the expectation is greater than 1. What we want is to ensure that the probability with which it will actually be the summation eta ij will be more than 1. Basically, the complementary event of the event that's complementary to this event is should be large. So the part that's left as an exercise now is to show, using Chebyshev's inequality, that this event, the probability of this event, is actually small. So which implies that the probability of the summation of eta ij's exceeding 1 is greater than or equal to 1 is sufficiently large. And if this, remember that if that happens, the algorithm will in fact reject the graph. So with this is with that we really come to the end of the second step in the analysis, and therefore also the end of the overall analysis. So if all of these work out, then the summation eta ij's will be greater than or equal to 1 with some good probability, which means that we have detected a collision, if you will. So that brings us to the end of our analysis of the property testing algorithm for bipartiteness testing that used random walks.